Hey, this is Michael. Today we're going to go over a tutorial on how to add an SDRAM to your 7 series FPGA that fits on one I/O bank, similar to what's done on the Arty boards. So there's a few tricks to doing this, and there is a big advantage in that you have just one I/O bank that's running at the SDRAM voltage, which is generally a lot lower than the voltages you're using for your other peripherals like 3.3 volts or 2.5 volts. We're going to use or target DDR3L SDRAM, and we'll launch into it with the block design. So the simplest way to set up an SDRAM controller is in the block design. I've already started by dropping down a microblaze debug module, an interrupt controller, and so forth, some local memory. And there's plenty of tutorials that show you how to do this. But let me show you the trick to the MDM, the microblaze debug module. We're going to use that to run a JTAG UART. So let me bop into here and just show you that I've enabled the microblaze debug module interface right there. I'm going to go ahead and hit cancel on that. And then inside the microblaze debug module that I've added, I'm going to enable the JTAG UART. And this is going to allow us to test our SDRAM later on without using any other infrastructure on the board. We'll talk directly to a command line interface running on the microblaze microcontroller through JTAG. All right, so let's go ahead and drop in what's called the memory interface generator, or SDRAM controller. Try to pull that over here, and I'm going to double click on this and start the configuration. So on the Arty board, we have a -1L speed grade. That's going to limit us to a maximum clock frequency of 667 megahertz. Now what the Arty boards do is they set up a SDRAM clock frequency of 350 megahertz, which then sets up a data rate of twice that, 325 megahertz, which sets up a data rate of twice that, which is 650 megabits per second on the data lines. All right, so right on the edge of the Fmax for the speed grade, the FPGA used on the Arty board. So let's step through the memory interface generator tabs. I'm going to create a new design, just one controller. I'll just leave this untouched. We are going to target DDR3 SDRAM. And now here's the first trick. This is a magic number, 3077. What that does is it gets us very close to that 325 megahertz clock frequency to the SDRAM. And that's also going to allow us to select a system clock frequency of 100 megahertz, which is the clock provided on the Arty A7 board we're targeting. And it's also a good clock frequency to use on any custom designs you might be working on. You notice that the clock ratio automatically went to 4:1. Now down here, the trick is to pick a Micron technology part that has a K instead of a J. Like that K designates a DDR3L for low power SDRAM. And I'm going to select this. This is the largest SDRAM, 16-bit wide, that can be supported on a single I/O bank. That's because the combination of the address and control lines completely occupy 2 byte lanes on the FPGA, leaving the other 2 byte lanes for the 2 bytes. And here I'm going to select 1.35 volts, so I'll make use of the DDR3L capability. I believe that this part can run at both 1.5 and 1.35 volts. And then for data width, because I could have multiple parts here, I'm going to select 16. We're using 1 chip. Leave the rest at default. I'm going to select the data width of 32 here because that's the width of the microblaze data bus running through the interconnect and so forth. No point going any wider there. And then here's the next trick. Input clock period. Having selected 3077 picoseconds as our SDRAM clock period, I can then scroll down and actually select 100 megahertz as our input clock, the clock being used to generate all the other clock frequencies used by the SDRAM controller. I'm going to leave the rest of this up. I take that back. For DDR3L, we want the impedance to be 40 ohms, and that is RZQ, which is typically 240 ohms divided by 6. And next, we are going to bring the system clock and reference clock in from I/O pins that are going to be shared with other logic. So I don't want the SDRAM controller inferring input buffers. So I'm going to select no buffer here and here. System reset we'll leave as active low. We'll leave that as default, and that is default as well. Termination 40 ohms for DDR3L. And then here is the next trick. If we pick new design, we are stuck with having to spread the address and control lines across 5 byte lanes, meaning we have to spread it across 2 I/O banks. We don't want that. This is not, we can't use this method if we're going to try to squeeze the SDRAM interface onto a single I/O bank. So we have to go to a fixed pinout, and we're presented with this. Now, we could go and individually select the bank number, byte number, pin number, and I/O standard for every one of these, but that's very painful. The best way to do this is to put this information into a user constraint file, the good old UCF format that was used by the older tools. And let me show you what that looks like. So it's a simple format. Our net name has to match the top level I/O port name. Location is the pin number, and then the I/O standard. For DDR3L, it's either SSTL135. For the differential signals, it's diff_SSTL135. All right. I think you can find this online, or you can grab a screenshot here. But that's what it looks like. And where you're going to get this information from is you're going to get it from your schematic. So you're going to have already assigned your lower byte, upper byte to byte lanes. Here the lower byte is assigned to byte lane T0 in bank 34. The upper byte is assigned to byte lane T1 in bank 34. And then the address and control lines are spread across byte lanes T2 and T3. One of the other tricks is to put the reset on either byte lane T0 or T1 because it won't fit. We need every single pin in byte lane T2 and T3 to fit the address and control lines for the SDRAM. All right, I'll show you a few more examples of designs which fit the entire SDRAM interface on a single I/O bank. Here's one. Once again, we have the 1 data byte on lane T0, another data byte on lane T1. Note that the order of the data lines doesn't matter, but you must put the DQS signals on the DQS pins for both byte lanes. And then the order of the address and control lines does not matter, but they will not fit unless you put the reset on one of the byte lanes used by the data lines. And there's one more trick, and that has to do with the VREF pin. So let's pop back into here. So I've already prepared the UCF that you see there, so I'm going to go ahead and read that in. And then validate it. And here's my first mistake. I forgot to check something, so I'm going to go ahead and go back. No, I don't want to save. Go back, go back. I need to check internal VREF to free up a pin or 2 pins on the banks I'm using for the SDRAM. So back here, fix Pinout, read the UCF, validate, we're good. So you want to iterate on this until you get it to validate. It's a good check. I'll hit next. I'm not going to connect these to specific pins because they're going to come from internal signal paths or be connected to internal signals. Next. I'm going to accept, next, and then generate. Now, I spent a lot of time trying to get this tutorial running on Vivado 2024.1. As soon as I hit generate, Vivado crashes over and over, no matter what I did. So I had to regress to Vivado 2022.1 to get this going. So here we go. We'll generate. And then I'm going to go ahead and run connection automation and let Vivado make all the connections. Maybe not all, but most of the connections. I don't like this here. I'm going to pull that back over there. All right. So it made a fair number of connections, but I don't like them all. I'm going to export that because I like to drive an LED with it just for debug. I'm going to export that but before I can do it, I haven't found a way out of this. I need to disconnect it. It feeds into this processor system reset block. So I'm going to disconnect it. I'll just delete that. I'll export it or make it external, and then I'll go ahead and reconnect it. All right. Now clock ref needs to be 200 megahertz plus or minus a megahertz or so. So somewhere set between 199 and 201 megahertz. So it can't be connected to our 100 megahertz clock. So I'm going to go ahead and disconnect that. And in anticipation of this, I've already dropped in a PLL that takes the, yep, clicked on the wrong thing there. A PLL that takes in the 100 megahertz clock and outputs a 200 megahertz clock. I've gone ahead and just selected PLL. We're just doing frequency synthesis. Doesn't need to be locked to anything. I have a locked output for better or for worse, and I don't have a reset. It's just going to free run. Cancel that because it's already set up. And let's see where that's connected. Ah, it's not connected to the right thing. Okay, I'll disconnect this guy as well. Alright, so Vivado doesn't always do the right thing. Let me go ahead and undock this. Gives me a little more space to work with. So I'm going to take sysclock and connect it to the 100 megahertz clock that I'm bringing into this module, and then I'm going to take clock ref and connect it to the 200 megahertz clock output. There. I'll go ahead and export this. It's my entire SDRAM bus, and I'm going to rename that because I've already named things at the top level, so I think I have to redock this to get that. There we go. And I'm going to rename it DDR3 underscore SDRAM. Gives me a nice name that I can make use of at the top level. I'm going to rename this because I'd like my DDR3 signals to all be prefixed with the same name. Makes them easier to find. And then I'll do the same here. Oh. Rename that at a DDR3 underscore. Okay, so I think I've got everything connected. I've got my MMCM locked. I'll drive an LED with that. Init calibration complete. I'll drive an LED with that. This will connect to external pins going to the SDRAM. And I'll show you a little trick here. We need the instance name of the microblaze further down the road when we get into Vitis. So it's nice to give this guy a name that's easy to remember rather than the default name, whatever that is. The name can't contain microblaze. I learned that the hard way. So I name it host CPU. Give it a name that you can remember, because we'll come back to this when we get into the Vitis side of this project. All right. So the last thing, now that we've completed our block design, is to create the wrapper. So I'll go ahead. Actually, that's not the last thing. Let's validate this and make sure. Yeah, it validates. And let's go ahead and do create HDL wrapper. And we'll just let Vivado manage that. And let's have a look at the wrapper. So there's our ports, I've went ahead and threw in an advanced peripheral bus interface just for fun. There's our 100 megahertz clock input coming from the outside world, and there are the pins that will connect to our DDR3 SDRAM, and we have a reset input from the outside world. The reset input and clock input are resources that are on the Arty board. So we have the reset pin is actually coming from this CK reset, which is coming from a push button in the upper right hand corner of the Arty A7 board. And then our G clock 100, our clock 100 is coming from this, which comes from an oscillator on the board. We can go ahead and Control C, Control F, Control V, and go ahead. So there's where our clock's coming from, 100 megahertz, and this is the push button that pulls this low to reset whatever you want to reset inside the FPGA logic. Okay, I'm going to close the wrapper, and let's just pop into the top level. For that, I'll go back to Notepad++, which I like. So I've instantiated the wrapper down here, connected the reset, the 100 megahertz clock. There's the connections to the advanced peripheral bus, and then the connections to the SDRAM. These signals go to the outside world, and these two signals, the MMCM locked and at calibration complete. I drive, there's 4 LEDs on this Arty A7 board. I drive 2 LEDs with these status signals. And this is just for debug. That's something we need to do all the time in our custom board and so forth. Right, so I think everything's ready. I'll go ahead and kick off a build, and we'll come back when it's done. This doesn't take long, but I'm sure you don't want to watch Vivado crank it out. All right, we're back. Vivado is completed generating the Bitstream. I'm just going to hit cancel here. So the next thing I'm going to do is to export hardware, include Bitstream. I'm going to export the XSA, the file that we throw over the wall to the firmware guys, the guys who are writing the code that will run on the microblaze. I'm going to drop this into the Vitus project, or Vitus folder that I create under the project hierarchy here. And next, finish. So I've generated that, and we're ready to move to Vitus. But there's one more thing we like to do for the board design guys, and that is to generate the pin delay list. This is a list of delays from the pin on the silicon to the pad on the package of the device. And the way we do that is we export, and I think I'm blowing it here. Let me open the implemented design. There we go. Okay, so we've opened the design in implemented form, and we can then go to File, Export, Export I/O ports, and I'll just take the, well, I don't take the default path, but let's just rename that so we can find it. There it is. We'll pop up one level here. Drop it into the root of this folder, ioports.csv. Okay. And then let's have a look at that file. So that file contains a min and max delay in picoseconds for every single pin that's used in the design. And so here we have all our DDR3 SDRAM pins. And what I'm told is you want to go ahead and use the average of these two. So add them together, divide by 2, and use that number. Okay. Give that number to your PCB layout guy so that he can do delay matching from the silicon all the way to the pin of the SDRAM. There's several documents that Xilinx provides. One is User Guide 586. The other is White Paper 484 that go into some level of detail on how to handle the PCB layout for DDR3 and so forth. These could both use an update. They've left out DDR3L or haven't updated it for DDR3L, but they do have a nice little set of guidelines on what the overall delay should be from package to package. Let me see if I can find that here. Here we go, delay matching of signal nets. And they're suggesting that your DQDM nets should be matched with DQS nets, so within a byte lane here. So the lower byte, upper byte, they're independent, but within a byte lane, you need to match within plus or minus 15 picoseconds. And for the address and control signals, you need to match within plus or minus 25 picoseconds. They're single data rate, whereas the DQ, DM, DQS are double data rate, so their timing specs are tighter. Now, I have to admit, I've done some designs where I haven't used the pin delay information. I've just matched the delay on the board from FPGA package to SDRAM package, and that's worked fine in a lab environment. If you're going to put your board into temperature extremes or environmental extremes, I suggest you go ahead and generate the pin delay list and use that information to match the delay from FPGA die all the way to the SDRAM package. All right, so we are done with the Vivado side of the tutorial. The next thing is to move on to the Vita side and show you how to generate a little project that tests the SDRAM interface on your new board. Have fun. Catch you later.